we present LightHeadEd, a method to capture relightable and editable Gaussian head avatars using a smartphone equipped with Polaroid filters. Our method creates texture head avatars with decomposed reflectance information in the form of albedo, specular roughness, and high-quality normals to allow for relighting in novel lighting conditions. Our novel textured representation enables flexible editing capabilities. For example, we can change the shape of the head avatar entirely while keeping the same appearance. Or we can modify the appearance via a text prompt while keeping the geometry intact. Reconstructing realistic head avatars generally require a Lightstage capture system for disentangling the surface geometry and appearance into normal, albedo, and specular component. Though thus systems model the dynamic facial reflectance and geometrical deformations accurately, they are extremely expensive and sophisticated, making them very difficult to scale to capture diverse demographics. Our work aims to democratize capturing and reconstructing relightable head avatars using a commodity smartphone. One of the key components of a Lightstage are the cameras equipped with parallel-polarized and cross-polarized filter arrangements to independently capture the illumination information in the decomposed form. Leveraging the same principle, we place a thin polarized film over the flashlight and two back cameras of a smartphone, one at a relative angle difference of 90 degrees with the flashlight's polarization angle to capture the cross-polarized video stream, while the other at 0 degree relative angle difference to capture the parallel-polarized video stream. The subject is captured in a dark room, with the flashlight of the smartphone as the point light source. We capture both the cross and parallel polarized video streams simultaneously. However, we don't use any stereo-based depth or tracking due to a very small baseline between the two cameras, treating both the streams as independent monocular videos. Once the polarized data is captured, our next goal is to reconstruct a relightable and editable head avatar of the subject. Unlike popular 3DGS-based parametric head representation, which suffer from surface noise, we propose a novel 2DGS-based texture head representation, where we embed all of the attributes of a 2D Gaussians in the UE space of flame head mesh. We now explain the proposed method to learn the decomposed Gaussian attributes in the form of UE maps. We start with densely sampling 2D Gaussians in the mesh space of the flamehead model. In other words, for each 2D Gaussian GI, we have an associated UE texel to store all the primary attributes of GI. All the UE maps are randomly initialized. We propose to learn the primary attributes using a set of hash-encoded MLPs, phi omega, which takes a UE coordinate of GI as input and predicts 2D Gaussian attributes omega I. We follow a two-stage training process, where in stage 1, the MLPs predict offsets, albedo color, tangent, bitangent, scale, and opacity. We transform each Gaussian GI defined in the canonical mesh space to the posed 3D space of flame head mesh obtained via skinning deformation with the mean position p hat I. We then add the primary offset to the initial mean position to account for details such as skin, beard, hair, etc. over the canonical head mesh. Besides primary UE maps, we also define a set of residual UE maps to handle pose or expression-dependent changes in the appearance and geometry. In order to provide expression guidance, we take expression parameters of flame head mesh and project them onto a k-dimensional space using a learnable projection matrix, pi, to obtain linear blend weights, w. The projected linear weights are then used to blend each basis residual maps in a linear combination to obtain a blended residual map, u delta. For each Gaussian GI, we query the residual attributes omega delta I and add them to the primary attributes omega I before shading and splatting. We also define a learnable cube map to learn the ambient lighting information of the environment during the shading. The shaded and rendered image is then compared with the ground truth cross-polarized input image, and the loss is computed for gradient flow, updating all the learnable parameters all the way back to the primary and residual UE maps. During stage 2, we only aim to learn the specular roughness, Therefore, rest of the attributes are simply queried from UE maps learned during the previous stage. Similar to stage 1, we add primary offset del I to the mean position p hat I. During this stage, since the albedo learned from cross-polarized images in the previous stage has a tint shift compared to the parallel-polarized images, we introduce a bilateral grid u theta to account for the same. U theta is defined as a learnable tensor which stores a linear transformation weight, theta I, corresponding to the u-v coordinates associated with each 2D Gaussian. The albedo, AI, is transformed accordingly to account for the tint shift, and the residual attributes, mainly specular roughness, are added to the primary attributes. Similar to stage 2, the Gaussians are shaded and splatted to obtain the rendered image, which is then compared with input parallel polarized images, and gradient-based updates are performed over all the learnable parameters till convergence.